To build a complex AI application, engineers often start with a God prompt, giving a single large language model, or LLM, a massive system prompt and a dozen tools, expecting it to run autonomously. It almost always fails. As the model runs, it feeds every tool output and intermediate thought back into its prompt. This quickly fills up the context window. The context window is the strict limit on the amount of text a model can process at one time. Without compartmentalized focus, the model loses track of its original goal, hallucinates, or gets stuck in infinite loops. Reliable applications require a different architecture entirely. Instead of relying on monolithic prompts, developers are orchestrating multi-agent workflows defined as state machines. LangGraph is a Python library that structures LLM loops as cyclic, directed graphs, using nodes, edges, and state. Nodes are individual workers, like an agent or Python script. Edges are communication pathways providing routing logic between nodes. State is the persistent data payload, updated by each node as execution moves through the graph. How you choose to share or isolate this state payload dictates the entire architecture of your multi-agent system. Treating multi-agent workflows as state machines gives engineers precise control over compartmentalized intelligence. To see how this works in practice, we can build 3 distinct graph topologies. This diagram illustrates our first topology, multi-agent collaboration. In this setup, multiple distinct agents operate on the exact same state of messages, meaning they share a single global ledger. If a user submits a prompt asking to fetch the UK's GDP over the past 5 years and draw a line graph, that payload enters the graph and initializes the researcher node. Once the researcher processes the query, a routing function evaluates it. It checks if the researcher wants to call a tool, generate standard text, or output a final answer, and routes execution down one of 3 conditional edges. If the researcher needs data, the router directs execution to the tool node, triggering a web search. The raw search results are then appended directly back to the global message ledger. When the researcher finishes gathering data and outputs standard text, the router passes control to the second agent, the chart generator node. To write the necessary Python code, the chart generator reads the entire accumulated global ledger. It relies on the raw data the researcher placed there to understand the exact context for the graph. The chart generator executes its Python code, returning a line graph of the UK GDP. It passes control back to the researcher, who evaluates the complete data and outputs a final answer state, triggering the end of the loop. Because every agent sees the exact intermediate reasoning steps and raw tool outputs of the others, this architecture yields highly collaborative results. But that shared global state comes at a cost. Piling every intermediate data pull into a single ledger rapidly exhausts the context window. For longer workflows, this becomes computationally expensive and prone to failure. This is the agent supervisor architecture. Instead of a share of ledger, this diagram shows a hub-and-spoke model. The central supervisor routes tasks to satellite nodes, and each satellite has its own completely private, isolated state box. We can test this by requesting a comprehensive research report on PFAS chemicals. That query hits the central supervisor node first. The supervisor's system prompt restricts it to a managing role. It evaluates the request, selects the appropriate worker from its routing function, and delegates the task exclusively to the researcher subagent. At this point, the researcher subagent boots up its own internal execution loop. It independently calls external search tools, reads documents, and processes information. All of this intermediate work, every search query and raw text snippet, remains completely isolated within the researcher's internal scratchpad. The broader graph network never sees it. Only after its internal work is complete does the subagent emit a single, clean, final answer payload back up to the supervisor. The supervisor reads that summarized response. Based on that clean data, it decides whether to route the state to another agent, like a coder, or to finish the execution entirely. By treating subagents as perfectly encapsulated black box tools, the supervisor model isolates state. This prevents prompt bloat at the routing layer and keeps the central agent focused strictly on orchestration. This chart illustrates hierarchical agent teams, which scales the supervisor concept up to strict fractal compartmentalization. A top-level supervisor node routes to entirely separate subgraphs, each containing their own internal supervisors and specialized nodes. We can push the system with a highly complex prompt, fetch internet data, write a detailed report on the North American sturgeon, and draw accompanying charts. The payload enters the top-level supervisor. The top-level supervisor parses the goal and delegates the massive data gathering phase exclusively to the research team's subgraph, waking up specialized internal nodes like a searcher and a web scraper. The research subgraph completes its localized task, formatting the raw data into a structured output. It joins this finalized state payload back to the top level, which then routes it directly to the paper writing team graph. This document authoring subgraph relies on a completely different system prompt and unique tools, utilizing dedicated outliners and editors to draft the final report without the distraction of web scrapers. When you run multi-stage nested graphs like this, execution can take several minutes. Debugging relies on clear visibility into the system's exact routing steps. This trace displays the complete 400-second execution for the sturgeon task inside LangSmith. LangSmith is an observability platform used to log and trace every step of an LLM application's execution. You can see how a single top-level user prompt expands outward into dozens of localized subteam executions, with all tool calls strictly confined to their specific branches. The trace proves the logic holds. The system sequentially fetched data, generated the chart, and authored the final report, bypassing the infinite loops and logic breaks that plague single-agent systems. By nesting subgraphs, hierarchical compartmentalization gives each individual language model a hyper-specific prompt and a tightly restricted toolset. This solves the context exhaustion of monolithic agents. This side-by-side comparison shows that designing effective multi-agent systems is strictly an exercise in system architecture. You deploy the shared ledger of multi-agent collaboration for tasks requiring tight generation, where agents must read every reasoning step of their peers. You use the hub-and-spoke agent supervisor for routing broad, distinct tasks, ensuring you don't exhaust the context window of your central routing layer with intermediate data. And you scale up to the fractal design of hierarchical teams for deep autonomous execution that demands extreme compartmentalization and highly specialized toolsets. Simply tweaking the prompt instructions for a single language model cannot solve complex, multi-step orchestration failures. Language models are inherently probabilistic. They predict the next most likely word. Developers must enforce rigid, deterministic control structures around them to ensure reliable outputs. Treating language models as interconnected nodes in a directed state machine is the essential architecture required to build scalable, reliable AI applications.